Hi, everybody, and welcome to our final and last part of this lecture. And what we're going to be identifying and looking at today is going to be pH. We're going to go ahead and see exactly what pH is. We're going to look at the relationships between hydrogen and hydroxide ions and how that is going to influence the pH level. So let's go ahead and start off by identifying exactly what pH really means and what do those values mean to us. Now, if you go ahead and look at this is going to be a visual representation of what a pH scale is going to be. Now, usually in a pH scale, we're going to have three things that we need to identify. We have one, our acidic range, two, we have our neutral range, and then three, we have our alkaline range, or in this case, our basic range. So we have our acidic range, our neutral range, and our basic range. And this might look really familiar based upon your previous schooling levels, but basically what you need to know is from 0 all the way to 6 is going to be considered acidic. 7 is going to be neutral. And then 8 all the way through 14 are going to be considered basic or alkaline. And the reason why we have this is because it has everything to do with hydrogen ions and hydroxide ions. So the more hydrogen ions we have, the more acidic something will be. The more hydroxide ions we have, the more basic something is going to be. The reason why we have a neutral range is because this part has an equal amount, so equal, of hydrogen and hydroxide ions. And the reason why we have these hydroxide and hydrogen ions is because of the dissociation of water. So remember, water is made up of H2O, and when we have a dissociation, so we're breaking these apart. So now we have a hydrogen and we have our hydroxide. Remember, dissociate. As we increase in the concentration or the amount of hydrogen leads to a more acidic condition. The more hydroxide ions we have leads to a more basic or alkaline solution. And when we have equal amounts, it gives us neutral. And that's why typically a pH of 7 is represented with water. Water is going to be typically neutral, or at least pure water. Water that comes out of your tap, drinking fountains, things like that, typically are around a 7. Reason why is because the state usually adds some minerals in there, and those minerals can kind of change it. But if you have distilled water, it would be at a pH of 7. So let's go ahead and continue with pH. Again, neutral is going to be a pH of 7. So this range right here, number 7, is always going to be neutral. Anything below 7 is acidic, and anything above 7 is going to be considered basic. And what you'll see here is I added a lot of different household items with their different pH levels. So you can see starting from our basic, we have bleach being very, very basic. Soapy water, ammonia solution, milk of magnesia, baking soda, and seawater. So all of these solutions have a much higher concentration of hydroxide. So as we move up, we're increasing in the amount of hydroxide. Once we get here, remember we have an equal amount of hydronium hydroxide. And then as we decrease, we have more hydrogen. So in this case, urine is going to be slightly acidic, black coffee, much more, tomato juice, orange, lemon juice, and then gastric acid, which is just another way of saying stomach acid, is going to be very acidic. Okay. And what I have here is the concentration numbers for water. The reason why, again, number 7 or the pH of 7 is going to be neutral is because we have 1 times 10 to the negative 7 moles per liter of hydrogen. And again, remember, in order for it to be a pH of 7, it needs to be equal. So we have a concentration of 1 times 10 to the negative 7 moles for our hydroxide, giving us a pH of 7. So again, the higher the concentration of hydroxide ions is going to give us more basic or alkaline solution. the more hydrogen we have, the more basic it's going to be. And then when we have an equal amount, it's going to give us neutral. One way I kind of remember our acidic is hydrofluoric acid is going to be very high in hydrogen. So it's an acid, so that's going to be much lower. So that's how I kind of remember the acid portion. And then as long as you can remember 7 is neutral, and then everything above that is going to be basic, you should be in a pretty good spot. So now I'm sure you're wondering, that's really cool that a lot of different things have pH levels, but Mr. Chang, what does that have to do with biology? What does that have to do with life? What does that have to do with what I want to go into? And the reason why that's so important is because pH levels can dictate many, many different things. So what I'm going to do is I'm going to give you an example of normal blood and abnormal blood pH levels. So everything in your body has a different pH level. Looking at this over here, you can see that all of our different fluids, which regulate many, many different systems in our body, have to have a specific pH range. So remember, everything wants to stay within homeostasis, meaning that they want to be in a very specific range in order to work their best. The reason why we want that is because, again, we want to make sure everything flows exactly the way we want it to. There might be enzymes within those fluids that only work in a certain range. And if we move out of those ranges, things might break down, they might degrade, or our enzymes might become denatured. And that's just a fancy way of saying that they'll get kind of destroyed. So you'll notice that pancreatic juices are at a 7.5 to an 8. We have our cerebral spinal fluid, tears, and interstitial fluids are all going to be at a 7.2 to 7.4. Saliva, 6.4 to 7. And then our stomach gases, 1.5 to 3. Now, what we're going to do is we're going to go ahead and take a look at our blood plasma, and we're going to see how pH levels can really affect how blood reacts and how important it is to stay within this 7.35 to 7.45 range. So we know that that range, 7.35 and then 7.45, are normal ranges. This is where we want to be. This is where blood is going to act exactly the way we want it to. It's going to be able to transfer nutrients and oxygen, do all this stuff perfectly fine. When we start increasing and hydroxide ions, and we start moving away from 7.45, so 7.46, all the way to, let's say, about 8, we enter something known as alkalosis. And essentially what that means is we are accumulating too much hydroxide ions. So this is going to be not a good range for us. We're not going to feel good. Our blood's not going to be doing the things that we want it to do. It might start affecting our veins, arteries, things like that. And it will definitely affect our effectiveness. Once we move even further, so we're really increasing in our hydroxide ions, we can actually experience death. And the reason why is because, again, our blood is going to be much, much too acidic, and there will not be any way that we can continue to survive with that level of acidity. Or, I'm sorry, with that level of base. And it's the same on the opposite end. If we take 7.34 and move down to a pH of 7, we are accumulating too many hydrogen ions. So again, that's going to enter us into a state known as acidosis. And again, same thing as alkalosis, it's going to be much too acidic. Our blood is not going to be running very efficiently. It's not going to be good for us. And then when we move past that all the way to a 6, again, we're accumulating way, way too many hydrogen ions, and we will experience death. So pH levels are all dictated between our hydrogen and our hydroxide ions. If we have too many hydrogen, it's going to be acidic. If we have too many of this hydroxide, it's going to be more basic. And remember, 7 is going to be neutral. So that's kind of to summarize all of this up. Now, there is a question at the bottom where it's asking about Coca-Cola and how it's an acidic drink at a pH of 3, yet our blood is roughly around a 7.4. So how come when we drink that, nothing really changes and our blood doesn't really become affected? And the reason why is because we have something known as a buffer. And a buffer is going to help maintain our pH within our narrow range or homeostatic range. So again, we want our blood to be around a 7.35 to a 7.45. And again, if there were to be major changes, again, we have those buffers to try to maintain this range. So it's not normal to see this change drastically one way or the other way because of those buffers. All right, and that concludes our lecture on pH. There is going to be one more slide after this test your knowledge slide, and it is going to be about cohesion, adhesion, and capillary actions, which I'm going to quickly explain. But as of right now, what I would like you to do is go ahead and try questions 1, 2, 3, and 4. So I'll give everybody a moment to kind of pause the screen, try those out, and then we'll go over those together as a class. All right, welcome back. And let's go ahead and check out question 1. So it says, which of the following substances has the lowest concentration of hydrogen ions? So remember, we have our pH scale. We know that 7 is going to be neutral. We know anything past that is going to be basic, and we know everything below that is going to be acidic. We know acidity, the higher the amount of hydrogen, the more acidic it's going to be. We know the more hydroxides we have, the more basic it's going to be. This question is worded a little funny because it's asking about the lowest hydrogen concentration. So in this case, what side of the scale is going to have the lowest amount? Again, in order for something to be acidic, we need to have lots of hydrogen ions. In this case, the question is asking for the lowest, so we know we're looking at the other side. So we want the largest pH number in this case, which will give us our lowest concentration. So we have a pH of 7, so that's going to be neutral, 13, 9, 3, and 5. And again, because we're looking for the lowest concentration of hydrogen, means we're looking for the highest concentration of hydroxide, meaning that B would be the answer for number 1. For number 2, it's essentially asking what's going on with bonds. So blank bonds form between the oxygen and hydrogen atoms with water molecules, where blank bonds form between different water molecules. In this case, we have covalent bonds. Remember those sharing. So we have covalent bonds here. And then remember, we also have hydrogen bonds because of those partial charges, because of the delta positive and negative. For number 3, Coca-Cola is acidic or is acid. When you drink cola, does the pH of your blood increase, decrease, remain the same? In this case, it would remain the same because remember, we have those buffers. And it's going to help maintain our blood from about that 7.3 to 7.4. So again, this buffer allows us to maintain our homeostatic range, so we don't have any major deviations from our pH, meaning that we're not going to enter alkalosis or acidosis. And then finally, a chemist has a solution of a pH of 2. So he adds a chemical to it, and shortly after, the solution has a pH of 7. Did the hydrogen ions increase or decrease with the addition of the pH 6 chemical? In this case, it went ahead and decreased. Again, the reason why is because going back up here, we're looking at the hydrogen ions, right? Hydrogen is associated with acidity. So we started off at a pH of 2 and we went to a pH of 6. So in this case, we would have decreased in hydrogen and we would have increased in hydroxide ions. All right. And this brings us to our last concept when it comes to water. Water does have some interesting properties. We have cohesion, adhesion, and capillary actions. So I'm just going to quickly talk about what cohesion is, adhesion, and then show you what that kind of looks like over here, as well as capillary actions. So when it comes to cohesion, it's just the attraction between water molecules to themselves. So cohesion, they're going to cohere, or they're going to come together with themselves. So we have our water, and then our water is going to cohere with each other. So an example of this is it's when we're looking at it as blood, it's going to allow blood to flow through our veins or flow through the veins. Versus adhesion, just like when you take tape and stick it onto something, it's got an adhesive, so you're adhering it to something. It's going to be the attraction between water molecules and the surface. Okay, so before this was water and water. Adhesion is water and then other or something else. So an example of this is between blood and the blood vessels. Okay, so cohesion, co, together, water, water. In this case, adhesion, adhere, just like when you take an adhesive strip or you take tape with an adhesive end and you're adding it to something else. You're taping it to something. In this case, water to something else. And then finally, our capillary actions. When it comes to capillary actions, they rely on adhesion from spontaneous flow of liquid, such as blood in narrow vessels. And capillary actions occur when adhesion to the walls is stronger than the cohesive force between the liquid molecules. So capillary actions enable the flow of blood through capillary beds. So this is going to bring us to these diagrams here. Essentially, what this means is capillary actions allow things to flow in a direction. So this right here is a very simple experiment. You can actually do this at home. If you'd like to do this, you just need 2 cups of water. One is going to be lower than the other. And then you're going to take a piece of paper and bridge it between. And what's going to happen is eventually they want to equal out. So they want to hit equilibrium. So they're going to both be about right here. And what's going to happen is capillary actions are going to occur. What's going to happen is the water, because they have cohesive and adhesive properties, are going to travel or flow to the other side in order to equal out. Again, remember, capillary actions rely on adhesion from the spontaneous flow for the spontaneous flow of liquid. So capillary actions occur when adhesion to the wall is stronger than cohesive. So that means this force is stronger than this force. And when we apply this to the human body, this is how capillaries are going to work. You can see that we have a flow from the heart through the artery, and then we're going to flow through here, through our capillaries and into our veins and out. And this is how we have oxygen exchange. So again, cohesion, water to water. Adhesion is going to be water to something else. Capillary forces, it's going to allow things to flow or liquids to flow when the adhesion is stronger than the cohesive force. All right, and just like that, that concludes our part 3 and concludes our lecture for this week. So remember, if you have any questions, comments, concerns, please feel free to reach out. Remember, Canvas is going to be the best and quickest way to reach me. And I hope everybody has an awesome rest of the day, and make sure to do the learning activities as well. I will see you in the next lecture.